So, now let us go to a sort of a comparison between the surface and volume integral approaches, right. So, the problem remains the same. I had some object V2 over here and some V1, and this was my current source over here. So, we started with the surface approach first. So, we are not going to redo all of it obviously, we just want to see conceptually where did the paths diverge in the derivation. So, what happened in the surface approach? What was the first thing that we did? We wrote down the Helmholtz equation for each region, right. So, for each region I wrote out, so let us call it n plus k n squared phi is equal to q n. Okay. These are all functions of space, I am not writing the bracket r explicitly. What else did we do? Apart from writing the this Helmholtz equation for each region, the other thing that I needed was Green's function for each region, right. So, del squared g n plus k squared n squared g n is equal to delta r r prime, right. And with these two equations, what did I do then? I multiplied one by g, the other by phi, subtracted them, but I never mixed the equations for region 1 or volume 1 with the equations for volume 2. I sort of solved them separately, and then I applied some theorems from vector calculus which converted a volume integral into a surface integral. That is how the surface S and S infinity came into picture. Integrals over S infinity vanished and I was left with the integral over S, right. So, each equation solved separately for each region. Okay. That is what we did, and our variables were, the variables that we solved were for were the E tangential and H tangential on S. Right. And finally, once we solve for it, we use the Huygens principle, right, to find the field anywhere. So, this is kind of like a revision of the surface integral approach, right. So, I mean this is not new. When we move to the volume integral approach, what was our starting point? Was the first step common to both? Right. So, what we did there was we also wrote down a del squared phi plus k n squared phi is equal to q n. But here, so for example, I got two equations from each region. Here, what was the difference? How did I do it? What was the starting point itself became slightly different. What were the two cases? We said with and without the object, right. We did not consider volume 1 and then volume 2. We considered with and without object. So, that became del squared phi I plus k naught squared phi is equal to q n, right. So, this is with and without object, and then what did I do? I eliminated the current source, right, and I got an equation in terms of phi minus phi I. Did I need to use the Green's function in this? Well, once I got the differential equation, the solution to it was written in terms of Green's function as a convolution, but which Green's function did I have to use? The one where V1, where there is no object, right, vacuum. If you remember that when I subtracted these two equations, I kept it something like this, del squared phi minus phi I plus I kept k naught squared over here, and then phi minus phi I is equal to whole bunch of terms over here. So, to solve this I used which Green's function? The one with k naught squared. That is what I had used, right. So, if I know the solution to this guy, this solution becomes a convolution of the forcing function on the right hand side with the Green's function, right. So, you notice the slight difference in approach, it started right in the beginning. In the surface integral approach, I went for each region separately, solved separately, subtracted. Here the entire volume is considered with and without object, and the difference is taken, and then I use my Green's function. So, Green's function is used in both cases. In the surface integral, I have two Green's functions, one for V1, one for V2. In the volume integral approach, I have just one Green's function, right. Okay. What else can we say about the differences? So, one thing was that in the surface integral approach, k1 and k2, they were constants, right. So, they were for homogeneous objects. Whereas, did I have that limitation here? No, right. Here my kn squared was actually k naught squared epsilon r function of space. So, I could deal with heterogeneous. These are the sort of the two contrasting differences between these two approaches. Nothing new here, we are just summarizing what we have already done. Okay. The differences do not end here. When I want to find out the field far away, I use in the surface integral approach, this is called my Huygens principle, right. So, the field at some point over here r prime is written as a sum of the incident field and this term over here, which is a surface integral again, and that surface integral includes phi and grad phi, which are E tan H tan on the surface. So, these are my secondary sources in my Huygens principle, right. So, we studied two equivalence principles. Which equivalence principle is this one? We studied surface equivalence principle and volume equivalence principle. So, this is clearly surface equivalence principle, because I have replaced V2 by a set of currents on tangential fields on the surface. So, it is a perfect example of a surface equivalence. Right. And in the case of the volume integral equation, again I have the field at some point is incident field plus scattered field. Now, this integral is over V2, that means I am going into the object. So, what have I done to the object? I have replaced this object by a grid of this sort, and at each grid point I have an equivalent current. So, this integral is saying sum over all of these currents. What is the current strength? Over here, right. So, this is the perfect example of volume equivalence principle, which we had studied earlier. When we look at antenna problems later on in the course, the reason why this is called a equivalent volume current will become clear, okay. But you can see that there is something in the volume which is being summed over, right. So, it is a volume equivalence principle that is used over here. Okay. Any other thing that sort of stands out for you over here? Which one will take more or less time to evaluate? The first one, obviously, right. So, surface is faster than volume, because every time you change your observer location r prime, I have to recalculate this whole integral. right, because when r prime changes, this Green's function changes, therefore the whole integral also changes, right. So, I have to evaluate over a surface, whereas the first one I have to evaluate over a line, right. So, that is the reason the surface is faster than the volume, but there are situations where, for example, you have a heterogeneous object, you have no choice, you have to do this. Yeah.
Which Green's function will be used?
This Green's function for k naught vacuum.
For
Vacuum. Why? Because when I massage these two equations into this equation, what I get is a k naught squared on the left hand side. So, this I should get the operator equation to be the exact same between what I have and Green's function. So, since it is k naught here, it is k naught here. Kn we already said is a function of space. So, this is going to be of not much use for me in calculating the Green's function. Right. So, now let us imagine that we are in the business of calculating radar cross sections for aircraft, ships and so on. Okay. So, you've got this code you have written which calculates the field at any point in space. Okay.